So student, I hope you have gone through this assignment and try all these questions. So I have selected some of question, especially from Fourier transform, discrete time Fourier transform. So we will try to do one or two question from this tube. So first I select this one. Okay. Okay. So we have to use Fourier transform. We have to find the Fourier transform, discrete time Fourier transform of this sequence. Okay. So we will try to do this. Okay. So we know that discrete time Fourier transform pair already. Okay. So I think you can remember if we have xn, this is time domain signal. Okay. And if we convert it to frequency domain by Fourier transform, it will be x capital omega. Okay. So this is the Fourier transform. Okay. And this is the frequency domain signal. Okay. And if you get the inverse Fourier transform, you will get again original time domain signal. So this is inverse Fourier transform. Okay. So I hope you can remember these identities. Okay. So we have first, if we get Fourier transform of xn time domain signal, okay, we have this frequency domain signal, capital X omega. So you can see that this is frequency domain. Okay. And the identity is here, the independent variable is n minus infinity to plus infinity xn e to the power j omega n. Okay, so this is the identity for Fourier transform. So this is time domain to frequency domain conversion. Okay, time domain to frequency domain conversion. Okay, so and we have also we have Fourier inverse Fourier transform pair, inverse Fourier transform identity. That is, if we get inverse Fourier transform of this frequency domain signal, okay, capital X omega, okay. So we will, if we get the inverse Fourier transform, f minus 1, this inverse Fourier transform, discrete time inverse Fourier transform, okay. So this is discrete time Fourier transform, okay. So this is discrete time inverse Fourier transform, okay. Discrete time inverse Fourier transform, okay. So if we get that, we will get xn, our time domain signal, and it is, okay. So you know that this xn is a discrete time signal. This is discrete time signal, and if we get the discrete, the Fourier transform of this discrete time signal, this x omega, okay, we can't say this x omega is discrete time, no? We can't say this is discrete time signal, okay. This can be maybe discrete time, or it may be continuous time. Most probably it is a continuous time function, okay. So this omega is a continuous variable. So we have integration here, okay, not a summation, okay. So we have integration here within 5 capital X omega e j omega n d. So this is the Fourier transform, and this is the inverse Fourier transform, okay. So here we have to use the Fourier transform, okay. So here we have to find the discrete time Fourier transform of this sequence xn. Okay, so we have to find discrete time Fourier transform of this xn sequence. Okay, so it is very easy. Okay, so we have, so if we get the Fourier transform of xn, we have capital X omega. Okay, so it is n minus infinity to plus infinity, but here it is minus 2 to plus 2. So n is equal to minus 2 to plus 2. Okay. So here we have xn. Okay. Here we have xn e to the power minus j omega n. Okay. So we have to calculate this sequence. So we have to calculate it from minus 2 to plus 2. Okay. So we have, so first minus 2, that means x minus 2 e to the power minus j omega minus 2 plus then x minus 1 e to the power minus 2 omega minus 1. Okay, plus 0 x0 e to the power minus j omega 0 plus x1 e to the power minus j omega 1, n is 1, here n is 1, and now x2 e to the power minus j omega 2. Okay, here 2. Okay, so I think you have to substitute this value to this point, then you can get the answer. So you can see here, this is 1 and this 2.5. Okay, this 3 1, this is 1, this is 1, and this is 1, this is 0.5, and this is also 0.5. Okay. So we can get x omega as x minus 2 means 1, no? X minus 2 means 1 at n is equal to 2. Here n is equal to minus 2. This term n is equal to minus 2. So here minus 2, it is 1. Okay, so here it is 1 e to the power j omega minus 1. That means we can minus minus plus, we can say 2j omega n, 2j omega. Okay, plus x minus 1. That means x n is equal to minus 1 state. That means x minus 1 is 0.5. So we have 0.5 e to the power j omega. J omega minus 1 minus 1. You will have plus. So it is plus j omega. Okay, plus j omega. And this is x is equal to n is equal to 0. That means 1, xn is 1. And e to the power j omega 0. That means e to the power 0, e to the power 0 means 1. No? It is 1. That means we have 1 here. Okay. 1 e to the power 0. E to the power 0 means 1. So we have 1 here. And x1 is again 0.5 e to the power here plus 1. So we have minus j omega. Okay. And you have x2 2. Okay, that means n is equal to 2. That means 1, x2 is 1 e to the power minus 2j omega. So you have these terms. Okay, so I hope we can use Euler formula if you want to do further calculation. Okay, I think it is enough for here. Okay, it is enough for this point. Okay, otherwise if you are not asking any other question, but if you ask to find, sometime you may ask to find the phase, the magnitude plot and phase plot sometime, okay, of this x omega. Okay, that means capital X omega magnitude and phase of capital X omega. Okay, sometime you may ask to find. Okay, if it is better to solve this further. Okay, because here you can see that we have several exponential terms. Okay, so at once it is hard to determine the magnitude and phase. Okay, so we have to use in Euler formula. I think if you use Euler formula, it is somewhat like this, no? If you use Euler formula, okay, E minus j theta, it is like cos theta plus, sorry, minus j sin theta. If it is j theta, you will have cos theta plus j sin theta. So you can see that you have real terms and imaginary terms separately. Okay. Okay. And if you write these terms in using the Euler formula in terms of cos and omega, cos and sine terms, you will have imaginary part separately, imaginary and real part separately, like this. Okay, and here also like this. Okay, and you can get all real parts together. Okay, and you can get all imaginary parts together. Then this can be expressed as a complex number with real parts and imaginary parts. So you have real parts and you have imaginary parts. So by using real parts and imaginary parts, you can easily find this magnitude and phase. Okay, so we will try to do it. Okay, so I am using Euler formula to further simplify this expression we got. Okay, this expression we got. Okay, so x omega, x capital X omega is equal to here e to the power j omega. So I can write it as cos 2 omega plus j sine 2 omega. No? So one thing I forgot to tell. So you can see that here omega in this expression, you can see this omega. Okay, so this omega is a frequency, no? It is angular frequency. So you have a function with omega. Okay, so you have a function with omega. That means this is a frequency domain signal. So independent variable is omega here. Independent variable is omega. Okay, so we have frequency domain signal here. Okay, now we are going to simplify it further to find the magnitude plot and phase plot. Okay, so I'm going to find these plots also. Okay, so you have cos 2 omega, j sine 2 omega, plus here you have 0.5 as cos omega plus 0.5 j sine omega. Okay, and here you have 1, okay, and here you have 0.5 cos omega, again cos omega, minus here minus sign is there, so minus j 0.5 sine omega. Okay, and these terms you have 1, so cos 2 omega, So here also it is minus sign. So here also minus sign, minus j sine 2 omega. So you can see that now this one, and this one, this one, all cos terms are real, no? So you can write them together. Okay, so you have one, okay, this one, then you have cos 2 omega, cos 2 omega plus 0.5 cos omega, cos omega, 0.5 cos omega plus 0.5 cos omega, another cos omega, and you have cos 2 omega, cos 2 omega. So you have real parts. This is the real parts. Okay, this is the real part. Plus you can write the here it is not plus actually. You can write minus here, minus j, all sine terms, no? So you have sine 2 omega, sine 2 omega plus here 0.5 sine omega, 0.5 sine omega. Here again 0.5 sine omega, 0.5 sine omega. Point 0.5 sine omega. And you can see that here plus sine omega and here minus sine omega. No? So here it is minus. So you can see that this term and this term cancel out. Okay. So you have sine 2 omega. And here again you have sine 2 omega. No? It is minus. Okay. So minus sine 2 omega. And you can see that this one and this one also cancel out. Okay. So you will have only real parts. No? So you will have only real parts, not imaginary parts. Okay. So please do the simplification by yourself. Okay. I hope I didn't do any mistake. Okay. So we will check it again. So here you have e to the power 2 omega 0.5 ej omega. Okay. 1.5 minus j omega. And e to the power minus 2 omega. Okay. Yeah. No? So here you can set cos 2 omega sine omega, 0.5 cos omega, 0.5 j sine omega, 0.5 cos omega minus 0.5 j sine omega. So minus j sine omega and this j sine omega cancel out. Okay. And you have e minus j omega, that means cos 2 omega minus j omega. Then again this minus j sine 2 omega plus j sine 2 omega cancel out. Okay. So you will have only real terms, no cos terms with this one. Okay. With this one. And you have only real terms here. Okay. So I think now you can easily find the magnitude and phase plot. Okay. So what is the magnitude? This is omega. If you plot x omega magnitude, okay, so you will have these terms, no? 1 cos 2 omega, 0.5 cos omega, 0.5 cos omega. So you have 1 cos omega here, okay? So you have 1 cos omega here, and 2 cos omega 2, no? So you have 1, 2 cos omega 2, cos omega. 1 cos omega plus 2 cos omega 2. 2 cos 2 omega. Okay. So you have this term, that means you have composite signal. Okay. So it is hard to draw. Okay. It is hard to plot because you have many cos terms together. No. So here you have x omega as 1 cos omega plus 2 cos 2 omega. Okay, so you have to plot this one like this, and you have cos omega like this, and you have 2 cos omega. That means it is like this. The frequency is twice than cos omega like this. Okay, so you have to find the composite signal, the all point added point. Okay, so it is hard to draw by hand, but using MATLAB or something you can easily draw it. Okay, so anyway, if it is hard to draw, okay, draw the plot, okay, it is okay. If you find the expression, that is okay. So the magnitude of x omega is nothing but this real parts, no? 1 cos 2 omega plus 1 plus 2 cos 2 omega cos omega. So this is the magnitude, and phase is 0, no? Because only real part is there. So phase is 0. So phase of x omega is 0. So if you plot the phase plot, okay, with respect to omega, so it is phase of x omega. So you will have 0. Okay, you will have 0. Right. Okay. So you can understand that how to draw the phase plot and magnitude plot for this kind of signal. Okay, I hope you can understand it. Okay.